Hello everyone, this is Yuechen Yang. This video is to give a paper presentation called Attention is All You Need. So this is a small introduction for this paper. The first one is that the paper proposed a new network architecture, the transformer, based only on the attention mechanisms. And the second point is that in this paper, the author uses two translation tasks. One is English to French translation, and the other is English to German translation. And these two translation tasks provided us the evidence that the transformer is more parallelizable and require less time to train. And this is the benefits of the transformer. Then about the overview, I will talk about the model architecture. I think this is the most important part for this paper. I will go through this slide quickly because there will be a graph later, and I will explain these things in that graph. I think it will be more easier to understand. So the first one is the transformer contains encoder and decoder parts. Each of them contains 6 identical layers. The second one is for encoder. Each layer has 2 sublayers. The first is a multi-head self-attention mechanism, and the second is a feed-forward layer. And the third one is the decoder is also composed of 6 identical layers. In addition to the 2 sublayers in each encoder layer, the decoder inserts a third sublayer, which performs multi-head attention over the output of the encoder stack. And the last one is an attention function can be described as mapping a query and a set of key value pairs to an output, where the query key values and output are all vectors. The transformer model in this paper uses the scaled dot product attention. So let's look at the graph. We already know that the transformer model contains 2 big parts, the encoder and the decoder. So the left side of the graph is the encoder, and the right side is the decoder. Let's first start from the beginning of the encoder. So the first is the inputs. The inputs will be sentences or words. And we know that the computer cannot directly learn the words. So that's why we need the input embedding layer. The idea is that the input embedding layer will use the embedding space, and it will map the words to vectors, and then our model can learn. So for the positional encoding, because like the same words may have different meanings if they are in the different position of a sentence, which means the position of words matters. So we want our vectors to contain the position information of the words. So that's why we need the positional encoding. And then the next step is to let it into the encoder block. And the encoder block is a very important component for the whole transformer architecture. Like besides the encoder block, we can see an N here, right? It means repeated, like because and also it means like stacks, like one encoder block is over another encoding blocks. And in this paper, the N equals to 6, which means the encoder parts contain 6 identical encoder blocks. And let's look at the inside of the encoder blocks. So for the encoder block, it contains 2 sublayers. One is multi-head attention, and the other one is feed-forward. So for the multi-head attention, uh, it just tells the feed-forward layer what to learn, because the multi-head attention can capture the different meaning of a word in the sentence or different aspect of a word in the sentence. I will explain multi-head attention more deep in detail in the like later slides. And then let's first talk about the feed-forward layer. And the feed-forward layer is very similar to the fully connected layer. Like we learn it a lot in the deep learning, right? And but be careful about that. The feed-forward layer is just where the learning happens, because we know that the fully connected layer will have weights, right? And the model can use backpropagation to update the weights, and then the model can have the knowledge and it can learn things. So this is one thing we need to care about. And then we can see like decoder. So the decoder is a big loop, right? The whole decoder is a big loop. So that's why like the bottom output is shifted right, because the bottom outputs can be the initial thing that we give to the model, or it can be the output from previous decoder outputs. Yes, and then again we need, similar to the encoder parts, we need to change them to vectors, and we need to add position information to the vectors, and then we will make them to the decoder blocks. And the decoder blocks contains 3 sublayers, and it also has 6 identical decoder blocks. So the top 2 sublayers are very similar to the encoder, but the bottom sublayer, which is the masked multi-head attention, is different. So why there's a masked multi-head attention? I mean, why there's a mask? This is because when the decoder learns, it can, for example, we want to translate English to French. So when decoder learns, it can see the whole attention vector for the English. But because we need to translate English to French, that means we should not see the whole attention vector to the French, right? We can only see the attention for our current translated French sentence. So that is why we want the mask. And then again, the multi-head attention and the feed-forward layer, and then to the linear layer, and we use the softmax to get the output probability. Yeah, this is like the big picture of the transformer architecture. So the next step for us is to look deeply to the multi-head attention. So this is multi-head attention. Before we learn multi-head attention, we need to first learn what is scaled dot product attention. So on the left side is the graph and the formula for the scale dot product attention. The graph and the formula are totally talking about the same thing. So the input of the scaled dot product attention will be 3 abstract matrix. One is query, one is key, and the other is value. So the first step is to make a matrix multiplication between query and key, and we scale them. And then we use a softmax function. And the last step is to make another matrix multiplication between it and the value matrix. And this is a scaled dot product attention. So for the multi-head attention, it just have like several scaled dot product attention. So this can make the model capture the different meaning of a word in a sentence, because we know that one word may have different meanings, so it can capture different meanings and it can color the whole meaning of the sentence. So this is multi-head attention. So about the critical analysis, the first one is the paper proposed a new model architecture, and it is only implemented in the translation. Yeah, in the model, it's only the model is only used to translate English to French and English to German. But nowadays we know that the transformer can nearly deal with any time series or like sequence data. So this is the first point. And the second point is that I think each part of the transformer could be explained in a more detailed way. Yeah, because this paper like introduced a totally new model, but this paper is, I think, it's a little bit short. Yeah, it can like write a little bit longer and go deeper, so it can make the reader more easy to understand. And the third one is the transformer contains two parts in this paper, but they can also be used in a separate way, such as the BERT, right? It uses the encoder part of the transformer, and the GPT, it uses the decoder part of the transformer. And the last one is that the author gives us like two benefits, like many benefits of the transformer. One is it can be parallelizable, and the other is it will use least time to train. And another benefits, like for me, is that the attention mechanism could make the deep learning model more explainable. Yeah. And then here's the resource link. Yeah, the original article and like some code with tutorial and the code demonstration and the repo. Yeah, that's all. Thank you so much.